All right, for today's video lesson, we're going to look at an old IB vectors problem from the retired tests. And this one in particular, it deals with vectors, and it's two-dimensional vectors, so it's not that tricky. The difference is usually we deal with vectors from an origin, and we describe them in terms of their horizontal and vertical components. But it turns out that a lot of really elegant geometric proofs can be accomplished without even having those components and just working with the vectors themselves. And so that's what the skill is they're trying to assess with this problem. Another thing to understand about these multi-step, multi-part IB problems is that oftentimes, if you look to the very, very last question, that is what they're trying to get at. In other words, they want you to have this kind of given information and eventually conclude that the point T, which was described as a 2/3 divider on this segment, they want you to know that point T happens to be, or prove that happens to be on the vector BM, where M is the midpoint of AC. So they're saying if all these conditions are in place, then if I was to draw a vector from B to M, it must go through point T. So that's sort of the big target. And they understand, the authors of this problem understand that if they were to just give you this and the given information, that most students wouldn't be able to get where they need to go in that amount of time. So what you have to understand in the back of your mind is all the little fun steps that lead up to part C are there to somehow help guide you in the right direction of being able to accomplish this proof. So that's what we're going to look at. So we have to know our basics of vector algebra so you can follow along with this particular proof or problem, because I'm not going to be able to explain the basics. For example, one of the basics that I'm not going to explain, but I will now, is that we can express AC as the difference between vector C minus vector A. So if I wanted to express AC in terms of A and C, I would just say C minus A. That kind of stuff we're going to have to accept as self-evident so that we can follow along this proof in a timely manner. So for starters, AC is the vector C minus A, as I said, and we were given information that AM is half of AC because M is the midpoint of the segment AC. So half of AC is half of C minus A, and I've got my step 1 down. AII, a little bit trickier. This time they're getting to the vector BM. So now we finally got to the vector that's supposedly going to be going through point T, but we don't know that yet. Of course, the picture, which is said to be not to scale, actually does sort of seem to work out, although we're not sure, so we got to prove it. Anyway, vector BM is going to come into play somehow, so they're trying to get us to express vector BM in terms of A, B, and C. And you know it's going to be part of your proof down here because they didn't just say express BM in terms of A, B, and C. They're already telling you what the answer is supposed to be. Now you have to kind of construct the proof and get there. So another skill set question, or a skill set that you need to develop is don't look at the thing that you're trying to, don't look at the outcome. Don't look at the outcome. Simply look at trying to express vector BM in terms of A, B, and C. So you can ignore the outcome until you do the work, and you should make sure that your work then is going to match up with this stuff up here. If not, you made a mistake in your logic or in your algebra. So I'm going to start off with BM as the sum of BA and AM. That should be pretty straightforward. To get from here to here, we can travel along the BA and the AM. Now, I knew I was going to involve AM because it's part of it, part 1. So I just now have to work on BA. AM is already given. Now we get to BA. That's A minus B. So we get A minus B plus a half C minus a half A. And some quick vector algebra. And it turns out, after I do all of this, I get the thing that they were looking for. A mistake that students often make, by the way, is they try to start here and work their way backwards. It's not a valid proof, and oftentimes it'll get you lost. So try to frame the question instead of show that. Try to frame the question in a way that you don't know what the outcome is going to be. And later on, you could use that to quick check your answers. Now we get to part B, and part B is just about the same kind of work or level of work as part A. This time we're going to look at RA in terms of A and B. So we find vector RA. Vector RA is, almost forgot where RA is. RA is going to be this little guy right here. And as you can see, you can almost start to see what's happening here. RA is a part of this, but you can see BR to RT. I bet you RT is going to come in here somehow. Since I have RA, I'll be able to do that. So what do we get? Well, we get that RA is going to be a third of BA, which is a derivation of some of this given information right here. And BA we can express as A minus B. So that's pretty freaking easy. It's just a third of the vector BA. We get to part 2, and we're talking about RT. Oh, look at that. Surprise, surprise. There's RT. And RT is given to me as 2/3 of RS. So I'm just going to write that down and see what happens. Now we got to figure out a way to express RS. RS, is the sum of RA plus AS. RA plus AS equals RS. So got RA was already expressed in the beginning. AS is 2/3 of AC. That was given information. And AC has already been found for us as C minus A. So you can see we're starting to put together all the information from the preceding work, and we get this equation. And this is generally, again, it's pretty straightforward algebra. You just got to be able to work with your fractions. So I won't show you how to work with fractions in this video. But it turns out that when I distribute my 2/3 of RS, and I have RS in terms of A, B, and C, I do get the exact expression that I was supposed to prove. Now we finally get to the meat of the problem, the thing that we're supposed to do, and what we're supposed to do is prove that T is on BM. The hardest thing for this problem is to get started. Where are you supposed to start? And the only thing I can think of is to try to use some of those segments and vectors that they asked us to find or express in terms of A, B, and C earlier, and just see what happens. So BT, for example, is the sum of BR and RT. I don't know if this is going to take me where I need to go, but I know I'm using some of the information that was given to me earlier. So I've got 2/3 BA, for example, and RT. Since I found BA earlier as A minus B, or actually that's just one of those self-evident things, and then RT was the thing that we were asked to find in the previous exercise. So that was from part BII. So now the good news is I've got BT expressed in terms of A, B, and C. And I'm not sure if this is going to do anything, but I'm going to clean it all up and see what happens. When I do all the arithmetic, I collect my like terms, and I discover that these are all sort of, what's the word? Well, they're all multiples of one another. Normally, if I wasn't looking ahead, I would just factor out a 4/9 and make this A minus 2B plus C. However, I recognize from earlier work that BM is half A minus B plus a half C. So you can see this is half of the vector that I ended up with right here. So I am actually trying to make that vector show up in terms of A, B, and C, and that's why I factored out the 8/9. So at the end of the day, we have this conclusion that vector BT right here is 8/9 of vector BM, which is really kind of what we need because we have two conclusions. The first is BT is a scalar multiple of BM, and what that means is it's going to go in the same direction. So BM and BT are in the exact same direction. Coupled that with the fact that they both contain the point B means that T must be on the line BM. Now again, if I left out this last part right here, then we could claim that one vector is here and the other vector is here, and I could claim that, well, this vector is clearly 8/9 of that vector, but it doesn't mean that the point T lies on the thing. But since they both share the point B, I can slide this over. If they were the exact same kind of vector, I could slide this over, and now because they're both sharing the same starting point, T must be on the vector. So that's the reasoning behind this proof here. Again, how are you supposed to know that? The only way I would have known to start here is I was trying to implement one of the segments or arrays, or vectors, sorry, that they gave us information about earlier in the problem. So, hope this is helpful. Have a great day.